Today we discuss area in the plane. This is not a brand new idea. So first let's start with what have we discussed or seen so far. So let's just say here F is continuous. I will just be working under this assumption for most of the day. Now, what have we seen? If the function is non-negative on the closed interval a to b, the total area bound by the curve and the x-axis, so in this case it's the area under the curve and above the x-axis between x equals a and b, this is just this definite integral. Okay, so this is one thing we have seen. And then we also discussed this, which is if the function is non-positive on the closed interval a to b, then the total area bound by the curve and the x-axis between x equals a and x equals b, well, in this case, it's the area above the curve and below the x-axis. Okay, what we remember from this is that the integral, the area comes with a minus sign. So the area here would be minus the integral from a to b of f of x dx. Or you could bring the minus inside here. Another way, which we mentioned, is it's integrating absolute value because the function is negative. So this minus sign, whether it's on the outside or the inside, it's the same thing as just integrating the absolute value. So these are two things we've seen so far. If the function is strictly positive or strictly negative, and we ask about total area. Now, one more thing that we have seen, and then we will move into sort of new and more ideas. And this is if you take any continuous function on a to b, that this integral from a to b of f of x dx, this gives signed area. And by that I mean, and I will draw an example that's very similar to one we did a few videos ago. If you have some function here, say this is 2 and this is 7, and the function is like this, okay, then if we know, for instance, the areas, this is area above, and this little part is area above, and then maybe in light blue, we have this part, which is area below. Now let's assign some values to these areas. Perhaps this has area 6, and this has area 2, and this has area 1. Okay, then for this function, the integral from 2 to 7 of f of x dx, well, we can calculate it using signed area. It'd be 6 plus 1 minus 2, which is 7 minus 2, we get 5. Okay, and this is what I mean by signed area, and this is also part of our we have seen. Okay, well, if we go back to 1 and 2, those said something about total area. So generally, and this is sort of starting what's new, if we want the total area bound by a function and the x-axis, and this is for a less than or equal to x less than or equal to b, Well, what would it be in this case? Because we see areas and we can we can look and add. Well, the total area, we just add up these numbers. 6 plus 2 plus 1. We get 7 and 2. We have 9. Okay, the total area is 9. And if you think about its relationship to the integral, the total area would just be this. We integrate a to b of absolute value f of x dx. Okay? And here, what would the absolute value of this function look like? Well, here it would look like this, and then the only difference is this negative part would be flipped up. This would come up here. And so you, in fact, would have 6, 2, and 1, and add them up, total area. Okay, so this is how we would generally calculate it. And I will mention, at the end of yesterday, we practiced integrating an absolute value. We have to break it up into a sum. So let's do some examples of this now. Here's our first example. We want the total area bound by the cosine and the x-axis for x in 0 to pi. And I can quickly sketch the cosine. I will sketch the cosine on its natural period of 2 pi because it's a little bit easier for me. I'm just used to graphing cosine on 0 to 2 pi, but then we're interested in the total area between 0 and pi. Cosine goes high, 0, low, 0, high, and then it looks like this. Okay, so what we want here is we want this area plus this area. We want to integrate the absolute value of cosine. So we want this 0 to pi, absolute value, cosine x dx. And just like the example that we ended with last time, the way we do that is we break it into a sum. So here, from 0 to pi over 2, cosine is positive. And we would just integrate cosine x dx. And from pi over 2 to pi, cosine is negative such that the absolute value of cosine x is minus cosine x. So we integrate from pi over 2 to pi of minus cosine x dx. Okay, and this here is, well, it's, maybe I'll put star equals, and this over here is star. Okay, I just sort of continued my line on this side of the board. But this is the total area bound by the curve, and it is this, the integral of the absolute value of cosine x, just breaking it to a sum of two integrals. Okay, well now we can use fundamental theorem of calculus for each one. We integrate cosine, we get positive sine. So this is sine x evaluated between 0 and pi over 2. And then here we have a negative cosine. This would be minus sine x evaluated between pi over 2 and pi. Okay, so here this would be sine pi over 2 minus sine 0, and then subtract, we have sine pi minus sine pi over 2. Okay? Well, these are not too terribly bad to evaluate the sine function. Sine of pi over 2 is 1. Sine of both 0 and pi is 0. Maybe I should write that. This is 0. This is 0. This is 1. And then this one is also 1. And so now what do you see we have? We have 1 minus minus 1 is 1 plus 1, which is 2. Okay, so this is the total area here, which is shaded in purple. Next problem, total area bound by 1 minus x squared and the x-axis for x between minus 1 and 3. And again, what we want here is the integral minus 1 to 3 of absolute value 1 minus x squared dx. Now, what we can do and what I recommend is that you sketch a graph of 1 minus x squared. You could also use your graphing calculator or Desmos to see a graph, because we're going to need to break this into a sum where 1 minus x squared is positive and where it's negative. Okay, so let's sketch a graph now. At 0, the function value is 1. At 1 and minus 1, we're at 0. At 2, 1 minus 4 is negative 3. And then at 3, we are at negative 8, which is down here. Okay, and then it's more or less, this is the shape of the graph, but the total area is this piece, and then plus the area here. You don't want to just integrate 1 minus x squared between minus 1 and 3. That's signed area. That would have this part coming with a plus and this part coming with a minus, but we want both this and this to count with a plus for total area. Okay, but we see how to break this up into the sum of two integrals. This will be the integral from minus 1 to 1 of 1 minus x squared dx. And then from 1 to 3, the function's negative, and so the absolute value is negative the function x squared minus 1 dx. Okay, this that I have written so far is, well, really the most important part in getting it right is to break it appropriately into the sum of two integrals based on where the function is positive and negative. Okay, so now let's continue. This is x minus x cubed over 3 between minus 1 and 1, and then we have x cubed over 3 minus x between 1 and 3. Here we get 1 minus a third, and then minus 1 plus a third. That's for this term. And then for this second part here, we evaluate at the upper and lower limits of integration, take the difference. We get 9 minus 3, and then subtract off 1/3 minus 1. Okay, what do we have here? 1 plus 1. We have minus a third minus a third. And then we have plus 6. And then we have, this is minus 2/3 with a plus. We get plus 2/3. Okay, so all together you see we have 6 plus 2, which is 8. And this gives us this total area that's shaded in purple. Next, we have the question or the topic of the area between two curves. So instead of just having the x-axis and a curve, we have two different curves, F and G, and we want the area between. Okay, well, let's first answer the question when f of x is bigger than or equal to g of x on this closed interval, a to b. Okay, so the picture will look something like this. We have a to b. We have one function, y is f of x. And we have another function which is less than or equal to f of x, at least on this closed interval, so maybe down here. And then the area that we are interested in is here. It's the area between the two curves. Well, the way we can figure out what this must be is very similar to how we first thought about area underneath the curve and bound by the x-axis, and that is the notion of a Riemann sum. So let's talk about this for a moment. What we can do, I'll write it over here, is we can subdivide this closed interval into n subintervals of equal length delta x, which is b minus a over n. Okay, now let's make n kind of small for my picture. Okay, here, n is 4 in my picture. And then, well, we have this partition. Right? And we can make this rectangle. Let's see, do I want to do a right? Let's do a left Riemann sum. Here. Okay, and similarly here, I'm doing left, so it'll be here. It would be here. And it would be here, okay? Now, what are the heights of my rectangles? Maybe I'll put this over here. If we sum I equals 1 to n, as I have written this, so in my picture, as I said, I have a left Riemann sum, which means I picked the left endpoints. So this would be, well, the areas of the boxes, of course, this width is delta x, but what's the height here? Well, the height is f of xi minus 1 minus g of xi minus 1, right? F of xi minus 1 minus g of xi minus 1, and it's x sub I minus 1 because I have used the left endpoints. Okay, so this approximates the area between f of x and g of x on this closed interval. And if we take a limit as either n goes to infinity or as delta x goes to 0, we get the actual area between f and g, okay? And we can see by this formula what would be the integral. So we get, and I have room for it here, the total area that I'm interested here. This would be the area in blue, bound by the curves. Well, it's the integral from a to b of f of x minus g of x dx, okay? And I understand this is small at the bottom, but we will do some examples. So what you see here, just looking at this, and what you can remember is we integrate and we take the upper minus the lower, and then we integrate from a to b. And this gives us the total area bound by the two curves. Here's an example. Let's find the total area bound by 2 to the x and y equals 4 for x bigger than or equal to 0. Maybe here I will start by sketching. Okay, here's 1, 2, 3, 4. So this would be the graph of y equals 4. And then 2 to the 0 is 1. 2 squared is 4. And then 2 to the 1 is 2. And this looks kind of like this. So this is y is 2 to the x. Immediately I see the closed interval a to b is the interval 0 to 2, and the area that I'm trying to calculate is this purple area here. Okay? So now we can set up an integral. Well, it is 0 to 2, and then we take upper minus lower. So this would be 4 minus 2 to the x dx. This value is the value of this purple area here. Now we integrate. Okay, maybe before I do, let me just recall. I'll put this in a box. If we integrate a to the x dx, this was 1 over natural log a times a to the x plus c. Okay, sometimes this is one that people don't always remember, but we are remembering it here. And if you forget, just as a comment, side comment perhaps, if you forget, you can always write a to the x as e to the ln a times x, and then you can perform substitution where the inside function is ln a times x, and you will get this again if you forget. Okay, that was just a side comment. But we will use this here because we have to integrate 2 to the x. Well, this is 4x minus 1 over natural log 2 times 2 to the x. And this is all evaluated between 0 and 2. This is 8 minus 1 over natural log of 2 times 4, and then subtract off. Well, this is 0 minus 1 over ln 2 times 2 to the 0, which is 1. So what do we get all together here? We have 8 minus 3 over natural log 2. And this would be the area here. Next example, find the total area bound by y equals x squared and x equals y squared. Well, you see, I'm not given a closed interval or anything like this, so perhaps I will begin by graphing. Y equals x squared. Let's see, here's 1 and 1 and minus 1, and it looks something like this. Well, what would the graph of x equals y squared be? You just take this and then go like this. So it's going to, we graph x as a function of y. I'm going to need something down here. Of course, this continues. I'm just graphing part of it. But this would go like this. So I don't know if you can tell the difference between these two shades of blue, but the one that's down here is x equals y squared. And you can kind of see the region that they carve out in the plane. It is here. Okay? Well, I need to integrate upper minus lower. So the interval I see, it's here. I'm integrating from 0 to 1, but what I need is this top, this dark blue, I need this as a function of x. And this part of it, I erased a little, but this part is the positive square root. So this part is y is the square root of x, okay? And this branch, which I'm not using, is the negative square root. But this is perfect. I have everything I need in order to solve the problem. So what I'm integrating here, 0 to 1, upper minus lower, and the upper function is square root x, and the lower function is x squared. Okay? And these are both power rule. We get, this is 2/3 x to the 3/2, and then minus x to the 3/3, and both of this is between 0 and 1. Well, we have very nice limits of integration because we evaluate these at 1, we get 2/3 minus 1/3. Evaluate at 0, you get 0. So this area here, the final answer is 1/3. Here, well, you see I have changed things a little bit more. Here, both functions, at least initially, I'm writing x as a function of y. And certainly I could solve y as a function of x, although in this one I would have both a positive and a negative square root part. But before I think about possibly doing that, let's graph these two. And one thing that we might want to do is figure out where do these two curves actually intersect. This will help me graph. So to figure this out, you can set the two expressions equal. Maybe I won't write that, I'll just do it. So you set these two equal. This will give you the y values they intersect, and then you could really use either formula to get the corresponding x values, and then you will have the point x comma y on the graph. Okay, well here we get 0 is y squared plus 2y minus 3, and let's see if this factors. We would have to have, oh, okay, let's do -1 and +3. And then they multiply to -3, they add to +2. And so we get that y is 1 and -3. Now, like I mentioned, to get the point on the graph, we can really substitute back to either equation. So the points will be, well, when y is 1, 2 times 1 is 2, and when y is -3, 2 times -3 is -6. Okay, so this is my work to figure out the points of intersection. And now, maybe I will try and sketch a graph of both of these curves below to figure out the region that I'm trying to find the area of. Okay, here are these 2 points graphed, and one of them is a straight line through the origin. Maybe I will do this one in brown. X is to y, okay? And then the other one, let's see, at when y is 0, x is 3, so that would be here. And then it's like a squared. X is a function of y, except it points down. So it will go like this. And then connect here. This is a basic sketch. Okay, and then the area that we want, we see it. It's the area between the brown and the blue curve. It's all of this. This is the total area. Let's look at this graph, okay? We certainly could integrate with respect to x. We would have to solve y as a function of x, and also upper minus lower. It's going to be a little bit complicated though, because if you notice, now let me draw a dotted line here. Here, okay, when x is less than 2, the brown function is the upper, the blue function is the lower. Okay? When x is bigger than 2, or between 2 and 3, you see the blue and the blue, they're both one, we have an upper minus lower. We'd have to write this y as a function of x, write this y as a function of x, and then do upper minus lower. And so we can do this. This is possible, but it would be a sum of two integrals. One would go from x equals minus 6 to x equals 2 of upper minus lower. And then the other one, we would have this, a separate integral for this upper minus lower. Now, it doesn't need to be this complicated. Let me now erase this black line, because you see, naturally we're handed x as a function of y. And if we think x as a function of y, we can still do upper minus lower. And it's easier here because, okay, get ready. You want to look at the graph with a different perspective in life, okay? And the perspective in life goes like this. Get ready. It goes like this. Where, now I don't want to block it, so where should I be? I'll be up here. This is upper. And this is lower. And if we do this, looking at it like this, you see this part is the upper function, this blue, and this is the lower function. Both x is a function of y, but we only have one integral because we have one upper, we have one lower, okay? We're not gonna have to break it into a sum of two things, and we already have these x is a function of y, so you don't have to solve y is a function of x at all. Okay, so let's do it this way. Sometimes it's easier to view it like this, as we see in this example. Now, what are my y values? Well, we see them here. Y ranges here. So this is minus 3. Oh, it's not going to look like that. Minus 3 to 1. So we will integrate. Y goes between minus 3 to 1, and then upper minus lower with respect to y. So this is what we will do, and let's do this now. Okay, here we go. We integrate minus 3 to 1 upper, which is the blue, minus lower, and then dy. Just like this. This one integral gives us the area of the purple region. This is 3y minus y cubed over 3 minus y squared, evaluated between minus 3 and 1. Okay, we get 3 minus a third minus 1, and then subtract off. We have minus 9. We have, this is going to be plus 9, and then we will have minus 9. Okay, altogether we have 2 minus a third, and then minus, this is minus 9, so plus 9. We get 11 minus a third, which is 10 and 2/3, or you can write this as 32 over 3. Okay, this would be this purple area, or the area of the purple region. The last question we want to address is something like this, where we want the total area bound by two curves on some closed interval, but on part of the interval f is above g, and on another part g is above f, like this. So the area that I'm interested in is this plus this, okay? And how could we calculate this? Well, perhaps the answer is not too much of a surprise based on everything we have discussed so far today. If this is the question, the answer is we integrate from a to b, absolute value f of x minus g of x dx. And in this picture, this would be, well, it would be an integral from a to c. Let's see, f is above g, or greater than g, so it would be here, it would be f of x minus g of x dx, and then we would add c to b. And on this interval g of x is greater than or equal to f of x. So it would be plus this c to b of g of x minus f of x dx. So this is how we would calculate the total area. And let's do an example here, and then that will be the end for today. We want the total area bound by cosine x and 1 minus cosine x for x in 0 to pi. And this is similar to the problem we did earlier, except now we have two curves, cosine and 1 minus cosine. We want the area in between. Let's begin by setting these two curves equal. So we set cosine x to be equal to 1 minus cosine x, and we will solve for x here. We get 2 cosine x is 1, or cosine x is a half. What is x here? Well, we're only looking between 0 and pi, and the cosine is a half at pi over 3. So this gives x is pi over 3. And then the point of intersection on the graph is pi over 3, comma 1/2. Okay? Now let's just sketch. Maybe I will do it here. And this time I'll try to only graph 0 to pi instead of 0 to 2 pi, which is where I usually graph the cosine. So we have pi over 2. And then this point, pi over 3, is less than pi over 2. Maybe this is 1, 2, and a half. So at pi over 3, a half is where these curves intersect. And cosine, it goes high, 0, low. Okay? More or less, this is y equals cosine x. And then we want 1 minus cosine x. So let's just plot a few points. We know it has to go through this. And 1 minus 1 is 0 here. 1 minus minus 1 is 2. This is kind of what it looks like. We have a basic shape and we have the basic understanding enough to set up the integral. And let me label this. This would be y is 1 minus cosine x. Okay, so the total area that we are looking for here is here and here. Okay? So we need the integral. It goes 0 to pi over 3 of cosine minus 1 minus cosine dx, and then we add pi over 3 to pi of 1 minus cosine minus the cosine. Pi over 3 to pi like this. And I can simplify these before I integrate. This is 0 to pi over 3. This one is 2 cosine x minus 1 dx. And then I have the integral pi over 3 to pi, and this is 1 minus 2 cosine x dx. So the sum of these two integrals is exactly what gives me the area, total area of these two purple regions. Now let's integrate. We get 2 sine x minus x, and this is evaluated between 0 and pi over 3. And then x minus 2 sine x, evaluated between pi over 3 and pi. Okay, we get 2 sine pi over 3 minus pi over 3. Then we subtract off at 0, but the sine of 0 is 0, and this evaluated at 0 is also 0. So these two are all we have from this part. now let's evaluate the second part. We get pi minus, well, again, sine of pi is also 0, so maybe I'll just write it this way. This is pi minus 2 sine of pi. Subtract off, we have pi over 3 minus 2 sine pi over 3. Okay, it's not too bad. Let's look at what we have here. We're almost finished. Cosine pi over 3, that we used, is 1/2. But the sine of pi over 3 is square root 3 over 2. Okay, so this is square root 3. And this minus minus is a plus, is another square root 3. So altogether we have 2 square root 3. And then we have pi minus 2 pi over 3, which is pi over 3. Okay, so this, maybe I'll put it in a box here, is my final answer. It is the total area here of the purple regions.